When we add a solute, like say salt, to a solution, what does it do to the freezing point? Well, I guess the title is going to help you a little bit. By the end of the screencast on freezing point depression, you should understand that when you add those solids to the solution, how does it affect it? Well, there's the answer right there. So, good to go so far. And let's quantify it. What is the formula that allows us to quantify that effect? We'll show that. No, don't worry, it would be given on a test. And finally, we'll see if it's a big effect. And I suppose the main thing is that, given a chance, you should find the worksheet and work out a lot of these problems, because there's several ways it can be given. We'll do one sample problem in this screencast 11.12. Oh, why do they salt the roads with calcium chloride rather than, for example, sodium chloride? There might be a reasonable explanation based on this understanding of freezing point depression. Let's begin. Screencast 11.12. Solutes lower the freezing point. Why? One explanation is that they might interfere with that crystal formation. A crystal is a highly ordered state. Throw in some solutes and they will occlude that crystal formation. They will make it more random, less ordered. So if you think about it, we're giving what you might call an entropic explanation for this phenomenon. More disorder when you add solutes. To quantify it, we use this formula. It's identical to the boiling point elevation formula, but with F's rather than B's. So, the freezing point depression, that is delta T sub F, which literally means the change in the freezing temperature. So that depression, it will bring it down. And once again, notice this is not the freezing point. It's just simply how many degrees it will go down, Celsius. It's equal to a constant called the freezing point constant. And these are some typical numbers here for given different kinds of solvents. Water has a relatively low effect. The other ones have a relatively large effect. Times M, which is the molality of that solution, so how concentrated it is, times this funky term here, the particle molality. By the way, there's the definition of molality. The particle molality is pretty simple. It's how many ions things break into. Sugar does not ionize at all because it's a non-electrolyte, so the particle molality is 1. Sodium chloride breaks in half right there. Its particle molality is 2. Calcium chloride, which, hint hint, is used to salt the roads, has an even higher particle molality of 3. Let's solve a problem based on this. What would be the freezing point of a 2.75 molal aqueous sodium chloride solution? One thing that should jump right out at you is they're not asking for the freezing point depression, they're asking for the freezing point. So you're going to calculate the freezing point depression and subtract that number that you get from its normal freezing point. And the freezing point of water is 0. So let's plug in these three numbers. Let's see. K sub F for water is 1.86, so that'll be that. The molality is given 2.75, and the particle molality for sodium chloride is 2. And there's those three numbers, 1.86, 2.75 times 2. I don't know why I didn't use parentheses there. Big number, 10 degrees Celsius. So the free answer is not 10 degrees Celsius since it's depression. It's negative 10 degrees Celsius. And so, is this a big effect? I'd have to say, yeah, this stuff is going to freeze 10 degrees colder. And, use this to make your ice cream, things like that. So a frozen saltwater solution can freeze water, since it has a lower freezing point than water itself. This is Screencast 11.12.